Hello guys, welcome back to TalkStriders. This is the third video of the finite element theory, in which we want to talk about time-dependent problems and non-linear problems. Let's go for it. So, let's go to the repository where we have the materials for the course. You can find a link in the description, or as I showed you in the previous videos, there are two ways to access the material. One is via the published video series and applied numerical computing, and the other one is via GitHub directly. So numerical computing intro, and yeah, here we go. So far, we have discussed the function approximation, which was actually the foundation of the finite element theory. And then we also discussed variational formulation and the reason that we need weak formulation and all those things. And then as the third video on this, which is probably the last video that I want to discuss finite element theory for now, because I said that I want to discuss I wanted to skip the high performance computing and preconditioning stuff and also the systems of equations. And as a result, we will have the time dependent problems and non-linearity in this video. These are the things that we need a lot in TalkStriders, but later on we will have dedicated series on high performance computing and preconditioning and using PET-C inside FreeFEM and Phoenix. But it is completely a little bit at least different from the finite element theory, and this is something else, so a little bit more advanced, and that's why I don't want to discuss it here. So let's start with time-dependent variational formulation. This is very simple, as I said before, because it's actually a combination of finite difference for the temporal terms and finite element for spatial terms, for the terms that we're dealing with space, and then that's it. And then all the techniques that we know before. So it's actually a combination of what we have learned so far, plus what we discussed in the finite difference videos. So let's start with that, and this is a type of time-dependent problem or transient problem that we have, like a temporal term derivative respecting time, and then in this case a second order derivative, usually representing diffusion from a physical point of view, and then some constants, can be reaction from a chemical point of view in this case. And then we want to see how we can deal with that. So again, we need time discretization. We apply, it's mentioned here, finite difference method to that. And then we need a mesh in time. So it's a sort of, dividing time into, similar to what we did in finite difference. It's really like dividing time into different time steps, into different time windows or time zones. And then we will have, like in this case, it can be a forward or backward Euler. In this case, you can see this is a forward Euler. We have already discussed this because we have the derivative. This is the unknown, but all the rest are actually in the previous time step. So we want to have like the value in the new time step as the unknown, and we can calculate it using an explicit scheme. And then we have a space discretization, which is done using finite element and variational formulation. So this is something that we already discussed. This is the famous finite element formulation. This is actually function approximation and use proper basis function. It can be like finite element. I mean Lagrange polynomials chosen as the basis function, it becomes finite element. And then variational formulation can be obtained using the Galerkin method or weighted residual method. We discussed this in previous videos. So for the spatial term, and then we reduce that actually the order using the integration by part and applying the boundary condition, we will have an equation like this. So the time, it's mentioned here that for time it can be a little bit actually the notation can be a bit confusing. It says here the unknown are written as Cj, so it's actually in the current time step. And then CJN, it means that the values that we know from previous time values. So in this case, this is something that we want to get, and this is something that we already have because we have the basis functions and we know the value of C at each node from the previous time step. So the equation that we had can be converted to something like this, which is actually, you know, after applying the time derivative. So it was here. So you can see that this is very similar to what we discussed before, because you know, this is this comes from here, so that it's written like for the time derivative we have un respective the derivative, partial derivative u respecting time. It can be written as like un plus 1 minus un divided by delta t. And when we apply that, so this term is actually something that you can see here, and this one is what you see for example for the rest of the equation actually, but most importantly here. And then we divide delta t to the right hand side of the equation, so that's why it appears here. So as you can see, this is something that we don't know, and these are all the things that we know, and this is something, you know, this you can see that delta t also appears here because we have actually multiplied delta t to all the terms that we had already. So this is something coming from finite element. This is finite element, but all this blue and the yellow one coming from finite difference. And so having this one, we can have like an equation that can be converted to finite element like this. So this is something that we don't know, multiplied by this is the basis function that we know, multiplied by Cj, which we don't know, and then these are the things that we know, delta t. This is, you know, another kind of linear form, and this one as well. So all these things are linear form, you know, because they contain the things that we already know from the previous time step, or from the initial condition if it is the first time step. And this one is actually the bilinear form. So we can easily compute A equals B, AX equals B, so A is this one and B equals this one. And as a result, we come to something like this. So this was actually the explicit Euler or forward difference for time, because you know, this is something that I said in the beginning of the video, that this is actually forward Euler. So in a forward Euler, this is what we have actually. So with forward Euler, we will have the weak form written as this. And then this is the mass matrix. M is mass matrix. This is, you know, that tree is mentioned here. The term comes from early days of finite element for a structural analysis. And this is the stiffness matrix, but this is not something that we call like that. But you can easily see here that the M matrix can be computed beforehand. And this is also something that can be computed beforehand. This is something that we will discuss later in Talks Writers, because for increasing the performance of computation, you can always you know, compute the coefficients beforehand, and if they do not change. In this case, if for example we have a variable alpha, which is the coefficient, the diffusion coefficient here, like that was actually something like alpha and then the Laplacian of u. So this is the diffusion coefficient. If you have it here as a non-constant, then it means that this the decay should be computed in each time step. But if it is not, then all these things are constant actually. So they we do not need to compute them in each time step. So this is the equation that we will have based on the explicit forward Euler. So the computation is quite simple. You can see that we can compute M and K from the beginning, and we don't need to change them. And this is an example using cosinusoidal, you know, basis functions, which are not finite element, you know, because in finite element we use Lagrange polynomials. But this is just for demonstration. And then when we have backward Euler scheme, which is the scheme that we usually use in Talks Writers, it has great stability in comparison to forward Euler. Euler. We discussed this before in finite difference series, that the reason behind this stability, it becomes something like this. Because this is actually the form that we have, because in this case you will have like the partial derivative equals to, you know, the current time step minus the previous one, and then the delta t, and then the rest of the equation is written as can be seen here. The rest of the equation is written in the current time step notation. As I said, this is something that we discussed before, so I don't want to go to the detail of that, but in the explicit format, in the explicit scheme, the rest of the equation is written in a previous time step, and that's why you need to really pay attention and take care of the stability. So the variational formulation can be written as easy as this. So everything in this current time step. So the things that we don't know, they go, the things that we don't know, they go to the right. The things that we know, that are known to us, they go to the right, which are this one. And then this term also comes to the bilinear term in addition to this one. So that's the difference between the implicit and explicit scheme. So in the end, it becomes something like this. This is a variational formulation. Now you know where they come from, and this is because we have like multiplying delta t to both sides of the equation. And then, we will have something like this. So this is very, very nice. If, for example, I told you, if you don't have any, for example, diffusion coefficient that is variable. So if you have a constant diffusion coefficient, you can have like this one computed beforehand as written here. So you can compute A. And then the whole, the right-hand side will be B. So this is actually B, and this is actually A, and this one is X. And then we have AX equals B, and we can solve the linear system of equation, and then we will have like the final solution. And this is for the boundary conditions. I don't want to discuss this, because I told you the boundary condition is something that the Phoenix and FreeFM usually take care of. What I want to show you is actually the PDF file that we discussed before. It is in the finite element series, Introduction to Finite Element, which we had already in Talks Writers, and in the episode 4 and 6 we had Phoenix and FreeFM. So this is the Wick formulation. You can find the link to that series in the description. But here is the PDF version that we had, a Wick formulation, and now after discussing all these things, we are able to fully understand all the steps here. So you can see that we define the test function and trial function spaces. And as I said, these are two important characteristics of this is for the test function space, this is for trial function, and then we need to discretize this using finite difference and discretizing this using finite element. So this is what we do. We multiply both sides by the test function, and then we start to integrate it. So for integration, we integrate both sides, and this one is second order. You can see that in the end it becomes like k, the Laplacian of t. So if it is constant, but so generally it's a second order, and for second order we discussed that in previous video. We cannot have like second order in the Wick form because the Lagrange polynomials, they do not have like a second order derivative because they are linear. And then we need to integrate, do the integration by part, removing these things. These are the things that we discussed. And then we use the green divergence theory to convert from a volume integral to a surface integral. We know that this is 0 based on the properties of the space that we had, like the properties of the trial function space. And then we discretize the time derivative using the backward Euler first order backward. You see that is mentioned here. Having this, we know Tn, and then we multiplied everything, and this is very similar to the kind of notation that we saw. So this is actually the bilinear form, and this is the linear form, which contains only the part that comes from here. So it is for the diffusion equation, but if it had like reaction, then we would have like more a longer linear or bilinear term, depending on a way that we wanted to discretize the reaction terms. So that's actually what we did in that series. I told you that later on we will have like detailed theoretical videos, and this is actually now very clear that what we wanted to do and what we have in the end. So that's for the time dependent problems, and let me quickly have an overview on dealing with nonlinearity, which is very important. Later on we will have some videos on nonlinear equations. So it's here, you know the definition of linear and nonlinear terms. Here we have like this is a linear equation, but this one is nonlinear because you have here x multiplied by itself. So in differential equation, if you have something like this, that you have the variable multiplied by itself, or it's an unknown function, or its derivative are multiplied by each other, then you have a nonlinear differential equation. So something like this or this. And then this is also nonlinear because this is sinusoidal. The sine function can be expanded to Taylor series, and you can see that obviously that this is actually a nonlinear one. So there are different techniques that we can deal with nonlinearity. One is explicit discretization. I don't want to go for this because this is not something that we use in tax writers. You can read this chapter later on yourself if you're interested. But we have I want to discuss the implicit schemes. So we have different techniques. We have one, the Picard technique. This is a very easy to implement one. And then we have relaxation, a single Picard, and then Newton method. So let's just start, with explicit. I don't want to start with that. I told you, but actually with implicit one, which are actually called also linearization. So for the Picard iteration, it is, imagine that we have a function like this. So this is for functions. Later on, we will have the concept for differential equations, but that's exactly the same thing. So for the functions, for example, a nonlinear function like this, this is actually the nonlinear part. In the Picard iteration, in the Picard technique, we define something an intermediate u. So another value of u, and then we rewrite the equation to something like this. So instead of having u multiplied by itself, we multiply u by the intermediate one, and we update this intermediate one iteratively. So we start with an initial guess for this one, then we solve the system, approximate a solution, or if it is a differential equation, we perform all the, for example, finite element approximation with formulation, everything. We solve the equation, but with an initial guess. And then we have, like, as you can see here, we perform the operation, like in this case, we solve this, but then we substitute the u into the intermediate u, and then we perform the operation again. So you can see that this is very simple to implement, and then what is really important is where to stop. So this is actually the kind of operations that I said, and the stopping criterion is we usually define a threshold, like in this case epsilon, and we say when the norm, in this case is a first order norm, or just a difference, is below the threshold, we should continue like that. Or if it drops below a certain tolerance or threshold, then that's the stop criterion for us, so we end. And there is another concept, a single Picard iteration, and it means that you just have, like, you substitute something like this, a nonlinear term in your equation, by something like this, and then you have like an initial guess that can come from the previous time step, as denoted here by that one, and then you perform the operation non-iteratively. You perform it only one, and that's why it's called a single Picard iteration. In a lot of cases, it doesn't make sense, but in a lot of cases, it yields to good results. So, for example, for laminar flows in Navier-Stokes equation, because Navier-Stokes is also a nonlinear PDE. This is something that we will discuss later on when we want to discuss fluid flow. But then you can use this single Picard iteration to deal with the nonlinearity if the flow is not complex. It's a laminar with low Reynolds number. And yeah, the next technique is geometrical mean. I don't want to go for that. And then Newton method. This is a bit complicated when it goes for differential equations, but the concept can be described here for a normal equation, for an algebraic equation. So it says that instead of having like just talking about u, we create a function of that. So the whole equation is encapsulated inside another container, in this case f. And then we have like a first order Taylor series that can be written as this. So this is really simple Taylor series defining u around u. This is the intermediate u. And then we have like, we know this equation. We know this one. And we have this one. And we compute the next iteration based on this. And then we add the next iteration to the current one. And then we compute this iteratively. As you can see, this is an iterative process. The problem for this equation, for Newton method, is you need to define, to derive the derivative of the function. For algebraic equations, it is simple, but for like ordinary differential equations, and even more important, partial differential equations, this can be quite challenging. But more or less the concept is like this, and it has a great convergence, a convergence and a stability conditions in comparison to Picard equations. So this is, you can see that we have f and then f prime, which is a derivative of f, and then iteratively we can update u to get the correct result. So you can see that we update u, so we compute this, and then we substitute u into u, the intermediate u, and then we go on. It can be also mentioned, it can be written also in this time dependent notation. But one important concept is relaxation that can be used with both Newton and Picard, and that's actually, this is also something that you can see in machine learning, a lot of algorithms in optimization. Machine learning, I think, is called momentum, but it is a very similar concept. So in this case, you see that, for example, previously we had always like u equals un, or intermediate u, when you wanted to iterate through all the process. But in this case, we have like, or the inverse, it doesn't matter really. So in this case, instead of applying that directly to u, we have like a parameter omega here that is usually between 1 and 0 that controls the amount of value that should be added from the previous time step and the value that is now computed as the intermediate. So in the previous steps, in the previous methods, in the original forms, it was always like we have a new intermediate u and we immediately assign that to u, or the opposite, as I said. But in this case, we define an omega, saying that, for example, do not do that because it can create some turbulence, some chaotic states in the numerical method. So we want to control that and do some baby steps toward convergence. And that's called relaxation in numerical techniques. And this can be applied with this technique, which is very simple to implement for Picard, that you define this omega and then you add omega, and so the equation for Picard becomes something like this instead of the one that you saw before. And for Newton, this omega is actually written here when you want to update u according to the previous value of the middle step of u. So this is a sort of contribution. Imagine that, for example, if it is half, it means that have like update u based on the previous iteration, just half of the things that you wanted to have to update originally. So it is actually like, instead of going like very, let's say, sharply to the next value, we want to have it like in shorter steps that can have better convergence. And this is the concept of a relaxation, and it goes for implementation. I don't want to consider this. I don't want to discuss this. So as in these figures, you can also see that how Newton is better in comparison to Picard. Although this is for simple equations and partial differential equations, you can easily see the effect. And then when it goes for ODEs and PDEs, that's the same concept. You can see here that, for example, for backward Euler, so this is for time discretization, but let me go for system of ODEs, the system of, so for this is a non-linear system of algebraic equations. It doesn't matter if it is a system or not, but you can see that here we have FU, and then this is non-linear. So with the Picard equation, that's the same. We define an intermediate U, and then we update. As you can see here, we solve this one using finite element, finite difference, whatsoever, and then we have, like in this case, this is a relaxation. You can see apply, and then we apply again. We have like U assigned to the intermediate U, and then we continue the operation. So that's very similar to what we discussed. And then in Newton, it is now we have a new term here, J, which is usually used for the derivative of differential equations. It's a Jacobian, because you have different components in a PDE especially, and then you need to define the derivative based on all the components that you have, respect to all the components. And that's why I said it's a bit complicated in PDEs, but the solution is more or less the same. So you have, like here, you need to solve this equation. So you solve this J for the delta U. You want to have like the value of the differences that you want to have in U computed. So you need to define your weak formulation in a way that it is written for delta U, and then you solve it based on the previous values, and then you update the new value of U based on the differences, based on the delta U, based on the changes. And with relaxation applied, but as I said, if you apply omega equals 1, then you don't have any relaxation, and that's why it's usually between 0 and 1. And if it is 0, then it becomes like, then it is not Newton. So that's really what it is. And then here you can see that you need to define your weak formulation in a way that the delta U is actually your unknown. The trial function is delta U. And then you can also combine these two together, and then this is a discussion on the stopping criteria. And when it goes to PDEs, you can see an example of a nonlinear PDE here. Again, anything is similar to what I described. This is for Newton. And then, so for, you need to write the equation in a way that, that the unknown is delta U, and then you update your the current value of U based on that. So this is what I wanted to discuss about nonlinear problems. I hope you enjoyed it and you find it useful. So I think now we are done with what I wanted to say about finite element theory. This is actually all the things that you needed to know. And I try to have it like in the shortest way, in the most concise way possible. I hope you enjoyed it, and then let me know if you have any problem with any aspects of this theories via the comments, or send me an email, and then we can discuss it more, or I can refer you to some other references. Stay safe. See you in next videos. Bye.